Now, thinking of things as having a dual nature, of being both a particle and of being a wave, really complicates life. And so we wouldn't really want to focus on that unless it actually allowed us to explain some things we couldn't explain otherwise. So here we're going to look at a couple of things that this dual nature can explain and how that really moved things forward. Now, the first one I want to start out with is something called blackbody radiation. Now, the reason that it's called blackbody radiation, something is called a blackbody in physics if it, and this is a hypothetical construction, if it wouldn't reflect or give off any light. So something would be completely black. It's absorbing light, it's not giving off anything. But if we start heating this black body up, it's actually going to start to create its own light. It's going to start emitting light. Now, that's something that's pretty surprising to us. When it gets hot, it's going to start to glow. Good examples of that would be a toaster filament. We've seen that happen. The filament inside of one of our old incandescent light bulbs. When you turn that on, you see that wire that's coiled up in the center start to glow. And it starts to glow white hot, right? Well, that's actually a really hot little filament in there. The reason that it's not burning out is that we don't have any oxygen inside the light bulb. Any little tiny fractures in there, any cracks, any tiny pores for little bits of oxygen to get in through will eventually cause the oxygen to start reacting with that filament and the light bulb burns out. And we've seen that happen before. Coals in a fire. These things are black until you heat them up and then all of a sudden they start to glow. That dark red, then more of a bright orange. Then if you really get them really hot, yellow, and maybe even white hot. The reason it's white hot is now it's giving off enough different colors that it looks like white light to our eyes. Now, high temperatures mean you have more heat energy, and it's going to be higher frequency light. Now remember, E equals h nu. E is the energy of the photon, equals Planck's constant times the frequency. So as energy goes up, so does frequency. Higher temperatures, we're going to start shifting from the red to adding more purple and UV in there. If it's a hot enough source, we're actually going to have ultraviolet start coming off of it. If it's a hot enough source like, I don't know, the sun, it's going to start to have ultraviolet come off of it. That's something that matters a lot, right? Now, in the wave view, that shouldn't be happening at all. We shouldn't just have heat start generating light like this. That's not something we were expecting at all. Now, here's another one, and this is one of the big ones that actually led to Einstein getting his Nobel Prize. People know about the theory of relativity, but it wasn't theory of relativity that got him the Nobel Prize. It was the photoelectric effect and explaining some of that. So he said, wow, hey, look at this. Photons that are above a certain energy can knock loose electrons, and that creates an electrical current, which is really useful for things like solar panels and some other effects that are out there. Detectors, if you're still using a CD player, you have a little laser, it reflects off of the CD surface, and the fluctuations in voltage, they have to be absorbed by something that turns it into an electrical signal, right? So photoelectric effect is something that's pretty important to us. Now, the ability made some sense, but here's what the wave you would expect. We can keep on having this wave progressing, and it can start to fill up this bucket, this mental bucket, right? Once it gets full enough, it should knock loose an electron. It should accumulate until finally it knocks loose an electron. And there should be a lag time with that while it accumulates enough energy for the electron to be knocked loose. So if I'm using really dim red, a really weak energy red light, dim red light would just mean there's few photons. A weak energy red light means that it's going to be, instead of 600 nanometers, it'll be like 650 or 700 nanometers, or even out into the infrared. So they're really wimpy photons. They're not doing it. So what do we have to do? We have to keep on hitting enough photons until finally this energetic bucket is full and it knocks loose an electron. It doesn't work that way. You can keep hitting the object with that dim red light over and over again and nothing happens. We use that to really good effect for a long time before digital photography when we said, let's go into the dark room. We'll use this dim, really deep red light so that I don't expose the negative, because the negative is supposed to react to light. Remember, that's what happened. The light from the scene that you're taking a picture of was focused, hit the film, caused a chemical reaction in the film, and made an image. You then were trying to develop it. You were putting it into chemicals, but you didn't want it catching any more light and having more reactions to change your image. So use this really far red light to make sure that it didn't happen. Good thing that we can't have the accumulation, because we would never have had photographic negatives work. We would have had to wait for the digital revolution, and, well, that would have taken a long time, and who knows if we would have tried making pictures. Now, here's the other piece of that. We would expect that there's no minimum energy. The wave should be able to fill a smaller bucket. In other words, we shouldn't be able to have that dim red light work for it at all. But here's the surprising thing. The photoelectric effect. If I shine a really dark red kind of light, and I'm using the very loose term, dark red, I'm talking about a far red or an infrared light. If I shine an infrared light onto a calculator's solar panel, the old way of thinking of it is, if it's a bright enough infrared light, I should power my calculator. Turns out it won't. You need something higher energy. You need to have something with enough energy per photon to knock an electron loose, with one photon doing it. That's kind of the idea of the photoelectric effect, showing that we need to use a dual nature in order to explain it. It has to be able to act as both a wave and a particle. When it's acting like a particle, we can't fill buckets up the same way. The wave doesn't just accumulate. So these are things that we were able to finally discover once we understood that light had a dual nature.